My name is Nicolas Kollerstedt. I'm responsible for Hedvig, the software-defined storage company in the Nordics and the Baltics and eastern part of Europe, as it is right now. And we will spend these 45 minutes talking about our software-defined storage platform, the heritage of that, and how it integrates with OpenStack. I will share this presentation with my colleague Tarmo. Tarmo is our technical expert in the region.
Hello.
And I will do a short introduction to really set the scene where we think the storage industry is about ahead in the near future and where we are right now. And just one or two slides about our company. So the industry, the storage industry, the enterprise storage industry is extremely large, as everybody knows. IDC predicts that it will turn around $40 billion annually on enterprise storage products. Data grows exponentially, as everybody knows. You need to store it. The traditional storage vendors have had their time, we believe, with their silo thinking of storage systems that is very hard to get rid of or get out of. And there's a matureness now in the market and a willingness to look into alternative technologies, especially when you look at the open source world, but especially, and even of course with storage solutions. I myself have been in the storage industry or the IT industry for almost 20 years, and what's happening right now is something phenomenal. Everybody has talked about the big paradigm shift that will take place sometime, but I think it's already happened. I remember 5-6 years ago when people were talking about what data to delete. We can't store everything because they're going to be too large. And that's not a question anymore, because I believe data is like, big data is like oil. Oil has a value, but the real value of it is, of course, when you can do something about it. Turn it into gasoline or plastic or whatever, then it's really turning into gold. And the same goes for data. So with all of this data we are capturing and saving and storing, when you can apply analytics parts to it or really look into it or do something valuable with it, it's going to be extremely valuable for companies. And that's what we see is happening right now. This is Gartner Prediction, so where we're going to head the next couple of years. So within 2019, they think we will have a 50% software-defined storage market in place. It's only about 10 today or something. 70% will be software-only storage products. And one very interesting thing is the 50% storage that will be acquired from companies that is younger than 5 years. So if you think about that, that's quite extraordinary actually, because all the traditional vendors will have a very, very big challenge, we believe, and also Gartner, obviously, to keep up with the changes and the demands from the market. This will, of course, affect organizations. So the thinking of bimodal IT, running IT organizations to take care of both the traditional storage or data or services is one thing that has been going on for a very long time. But the big challenge is when you need to handle two separate organizations to really move somewhere and be agile and fast moving in a new world and with new technologies to really deploy services and apps and other things in very high speed. And this is a big challenge, of course, on a management team, but also if you look at the infrastructure managers and the guys who are running the data centers, they're also struggling. And which way should you choose? So we believe, we look at the traditional storage as silos where you pretty much are locked in some way or form. You have specific systems for specific services, and when you are trying to move away from it, it could be quite challenging, time-consuming and hard to migrate and so on. There are some new solutions out in the market, new ideas like hyper-converged platforms, where you have one big data center in one box with compute power, network, and storage capabilities. And that probably solves a lot of things. But I strongly believe that that's also a lock-in. That's another type of silo, because if you outgrow one part of in that stack, you need to upgrade the whole system. You need to buy another box and another box, and you will be locked in. And that's a challenge for many companies right now. We do hyper-converge, but we also do what we call hyperscale. And that's the ability to scale out in another type of way that we will explain how it works together with OpenStack. So our company is a very young company. It's a Silicon Valley-based startup. We came out of stealth mode in March, I believe it was, last year. Our founder, Avinash Lakshman, is a quite well-known figure in the Silicon Valley community. He has no real storage background to talk about, but he started his career at Amazon, creating or writing the Amazon Dynamo platform. That was very successful. So his whole career has been into web scale solutions. In 2007, he was recruited directly by Mark Zuckerberg to Facebook as number 32 on their engineering staff. And his task was to redo what he did at Amazon, and he locked himself into a room and created Cassandra. So he's the father of Cassandra, that is well known, very well used globally today. I think it's 3,000-4,000 customers globally that use this. Many hardware vendors use it. Nutanix, for example, has part of Cassandra in their platform, and so on. But what he did see during this journey was, of course, the legacy in the traditional storage didn't keep up. So he thought, if I can apply this thinking to an enterprise storage environment, that will probably be very beneficial. So in 2012, he started to develop, together with some of his former colleagues, the Hedvig platform. And the idea was to build a scale-out software architecture, to build with native multi-site replication and no single point of failure, build an automated platform to really handle all the things you could expect from enterprise storage solutions in one same platform. And the idea was to run this on any hypervisor, any protocol, and in a multi-tier and a multi-cloud solution. So that's the whole fundamental idea of the Hedvig software-defined storage platform. So some of the features that was launched from day one was, as I said, the traditional enterprise storage functionality that you suspect should be in there, like deduplication, snapping, and replication, and so on. But also, one important thing is to really be able to consume this in a smart way. There are solutions, software-defined solutions, that is open source, of course. But what we experienced is that large enterprise has a little bit of a hard time to, when it comes to storage in particular, really depend on the open source community when it comes to developing new services. So we have a very tight cooperation with open source platforms, of course. But when it comes to our product, is an enterprise product that is perpetually licensed. So you own the license forever with all the capability, all the functionalities built in from the beginning. So with that, I would like to hand over to Tarmo to explain a little bit more in a technical way how it works and how we run this. Thank you.
Thank you, Nicolas. So to start, we need to somehow put the name tag to the solution. So we need to define what is the software-defined solution as such. So basically it is a bunch of servers that you can take out from yourself. We prefer there are some hard drives in these servers that you took from off from the shelf. Some SSDs as well for a caching. These are needed. But the servers itself are nothing really unusual things that you don't find, and kind of like a relatively cheap solution as well. So then you lay software on top of it, and it forms one big cluster of resources, of capacity resources that you can provide to OpenStack or orchestrate with an OpenStack with Cinder for a block storage, Manila for a file storage, or object store for with Swift drivers. What is important in software-defined storage is that it has to be really decoupled from the commodity hardware, the servers. So that's an entirely different thing, which we should not have any relations to the servers. It means that we can have different vendors or flavors of servers in the same cluster, and offering the capacity from different hardware, from different hard drives. We should not be, or a software-defined solution should not be tied with the hardware itself. The software-wise, it has to be distributed. So the software-defined storage solution has a value when it is truly distributed and offering and really the application focused, which means that we can create the storage policies which are fitting or suiting to our applications very nicely. And of course, nowadays, who would like to deal with complicated hardware or storage configuration activities, it has to be automated and API-driven, so the customers or applications can actually, ideally, even make a storage provision for themselves. To understand perhaps our solution a bit better, we would like to spread the storage to data platforms. So one thing is, one important, the storage important part is obviously the data layer itself that offers the block storage, file storage or object storage to OpenStack environment, let's say with a block storage with a Cinder, Manila, Swift, as I told before. And we have then a requirement also for something like a backup and a replication, maybe some additional disaster recovery sites, or disaster recovery requirements. In larger environments, this often needs, 6, 7, 8 of these blocks. On top of that, we have our application layer with bare metal, with the containers or services, or VMs for a KVM environment. Also, we can use it as a cloud, in a cloud. Some services that are using the storage solution. And then on top of it, we need to have some sort of like orchestration layer, which can be OpenStack or VMware, Microsoft, Mesos, Kubernetes, just name it. Today we had also a quite nice discussion about the UU even. Why not? So that's kind of like a infrastructure stack that every company has usually. We obviously are not, or not obviously, we are actually more interested of offering the storage service. So we thought it would be great to create something like a universal data plane type of thing. So we don't need to separate these services, that, you know, the backup service or replication service or these different services. We would like to have or see it as a one big storage cluster. So what it gives to us is that if we distribute data across this universal data plane, we would be able to protect our apps globally, because the data is global within this cluster. We can use components of, or we can actually service our storage from the cloud and create nice flexibility to services or workloads to move from one to move between the different tiers, different storage environments, I would say, different data centers, different clouds, to really get rid of the cloud lock-in and have this flexibility to service application from anywhere that we have or can. So why is this solutions different? First of all, that's again the environment for services, for applications. You need to have a OpenStack controller node, which is driven or orchestrated by Swift or Cinder, and then some, let's say, little interface that you can manage the whole solution with a Horizon, in example. And we have this, let's say, 4 data center solution. And we have this one nice storage cluster in here to serve capacity for the services. So we have a data center A, data center B, data center C, and we have a 4th one, data center D, if you will. We can say it can be or reside in somewhere in the service provider, in the cloud services, in the cloud somewhere, I don't know, Amazon, whoever the provider can be, and we should be able to access this data from everywhere. So basically the software-defined cluster offers us active connection to our data from everywhere. In example, we have an instance in data center A. We would really like to move it to data center B, whatever the reason is. Maybe we have more resources available in there. So we can easily take this instance and move it over to data center B. We don't need, before moving this instance over to data center B, we don't need to move the data or migrate the data over the data center B. It's already done. It's already there, because the data, the distributed storage solution distributes the data as soon as you write it to the storage cluster. It distributes it across the data centers or nodes, depending on your storage policies or data availability policies. Right. What are the typical software-defined storage components? First of all, the main component obviously is the storage service, the storage software itself, which is the component that does all the heavy lifting. It hosts the metadata, or tracks the data of where data stores are being data blocks are being stored. Obviously, it also stores the data to HDDs or SSDs, or actually offering the storage capacity to the applications and the services, and also it offers the classic storage services, or I would say even enterprise storage services like replication, deduplication, auto-tiering, cloning, snapping, all these things. So this is the storage tier. Then we have something which enables us to access the storage tier, and this is the access software. If you see the cogwheel, the orange cogwheel in this application hosts, we call it as a proxy between the storage and the application. So basically, we speak the storage the access software speaks the storage protocol language, and then translates it to OpenStack for a Cinder or Swift, and basically enables the data storing and retrieving service or information storing and retrieving for the applications. Also, it hosts the local metadata. So basically, if we need to understand how or where we should put this data, that information is used in or it hosted in access layer, access software. Then it offers, as I said before, the direct traffic from the storage between the storage and the cluster, and besides being just the dummy storage proxy, it has some intelligence also built in by providing the client-side caching, which means that if this lightweight access software sits close to the applications and caches all the information in the application level, close to the applications, then it basically enables the next read to recently stored data to be as a local. This is classic hyperscale approach. We have a storage layer in the bottom and access layer in the top over there. The hyperscale is flexible in a sense that we do not depend on each other. So basically, we can independently expand our storage tier and our compute or our compute tier. We do support also something called hyperconverged. What is it different? Why is it different? What is different in hyperconverged is that the access layer or access software has been served by same nodes or hosts or servers, if you will, as storage nodes. So in that case, if we need to expand our cluster, our storage cluster, we will also expand our storage or compute tier or platform or servers power. Right. So how does the I/O going or working in this software-defined storage solution? I will split it apart. Did split apart in here the access tier or access software from the storage software to show you the hyperscale environment. It's way easier to explain it in that way. So basically, if we issue the write from it goes from Cinder or Swift, it goes through the access software or through the proxy, and it writes down to the first node in a storage tier. So we have a copy of the data already in a cache layer, then in a storage tier, and then we will copy also to the nearest or closest host or node in the storage tier to have like a second copy of the data, and then we will acknowledge back to application. So please give us next write I/O, and in a backend, we are going to create as many copies as we need by replication factor. That is a background process. Well, it's not anyway related to the writing or to the front end, to the compute tier at all. And we will actually, all right. It's being written. I mean, if you have let's say several data center solution, we have 3 data centers in example. We can have 2 data centers close to each other. There is a synchronous distance between these 2 data centers, and the third one can be further away, like hundreds of kilometers away. So we can do the first write to our local data center and do this data replication to the next data center, and then have this third one copied over like asynchronously, which means we have this data still available in all these 3 data centers, but we are accessing only from 2, let's say, local data centers. Yes?
In what point in this scenario you say, do you do the acknowledgement? Well, what do you count as quorum? Is that the first write in the first data center and the second one, which is in synchronous?
That is how you define it. In a case, let's say replication factor 3, we do acknowledge back as soon as we have a majority of quorum stored in a storage array. Sorry, not storage solution. It's not really an array. So we do store the data to the local cache of the server. Then we will do the state. We also store the data to the first storage node in here. Then we basically have 2 copies already. If you need to have a more resiliency of your data, then we consider the quorum as going to be stored in the first node and the second node, and then we're going to be acknowledged back to the server this data. How does the read work? To reduce the latency, the read is being done from the closest node, or let's say node that has a recent, I would say closest node from the cluster. So basically, and then it will be, unless of course it's not the most recent read IO, which is not stored in the access in the proxy node. So read is not going to be done from all nodes. It's just done from the one of the first node that has the data available. If we have a multi-datacenter solution, we can have a read from different data center as well. So it's not really related to that tied to the data center itself, unless you say that this data is something that needs to be stored in that one data center only. In that case, of course, the read will be retrieved from there. However, you can still access this data cross data center over the cross data center link if you need to have this data also accessible from the other data center. But that's in case you just use only one data center that does store this data. Right. Software-defined solution needs sort of like a scalable abstraction, or sort of like a analogy for the LAN, if you will, to provide to applications and the services. So it means that you will create or build the bunch of metadata, or which defines the LAN size, or this virtual disk size. We call it as a virtual disk for any of the protocols that we have that can be supported, like block or file or object storage protocol, iSCSI in the block storage case. As we just create the metadata information, the provisioning is really fast, so we do not do any provisioning in the back end physically. It's the therefore it's a thin provision. So if we create the vDisk, which is 100 gigabytes of size, we actually do not reserve the space in the hard drives. We basically create in the metadata the size of the disk for 100 gigabytes, and then as soon as we start to write the data to the vDisk, then we start to use the actual capacity from the storage nodes. So therefore we are sort of space efficient. Then also we define the enterprise storage functions which to the vDisk, which are suitable for the applications. So certain applications, they need to have a certain access policies or replication factors and these things. And we can also, in the metadata level, can create the snaps and the clones, which creation, therefore, is also relatively fast. We do not need to wait data synchronization or these things. We just create another pointers to the data and start to move the data. Well, do not and this data movement or static blocks that we need to that will be changed by the application will be copied by the role of the storage nodes. I'm sorry. We basically create just the pointers to the new place. So in the front end, you don't even actually understand what is the.
So are there a variety of storage implementations that are writing drivers to support this, or are you doing all this from the data path?
I'm sorry.
So do you have a variety of storage implementations, vendors, so you're avoiding the lock-in, as you were explaining in earlier slides? Are you doing this based on them writing drivers to support your interface that you have here, or are you doing this all based on the data path? So you are initiating the copy on writes on your system based off of the storage of whatever the underlying storage is.
You ask if we use underlying storage.
Yes, because if you're supporting Cinder, then you're supporting a variety of storage implementations in order to do that.
Yeah.
So you yourself are another storage implementation in between. So you are thereby in this data path, yes?
We actually prefer to do it the way that the underlying, if you're using underlying storage as another storage array, we prefer to use it as a rather JBOD.
So then my question would be, what would be the point of using this instead of just using Cinder, which supports these features with 86 different drivers already?
You probably won't go for such a solution, yes. In that case, if you have a solution in place.
But why would I put this in front of Cinder then? Because, I mean, you gave the case where it's, maybe we could take this off here, but you made the case between you can support both object store and block storage being a single data plane.
Yeah.
However, though, you're touching on a variety of block storage reasons. No matter what, your application is going to have to support how you store things in object storage. You're going to have to write support in how you do that for block storage. So no matter what, you can't really abstract that of writing data, because you got to do puts, you have to do gets when you're dealing with object storage, and when you're writing to here, you're just dealing with a descriptor of some sort. So what exactly would this gain me by putting this in front of Cinder?
Can we take it offline?
Okay, sure.
Yeah.
Yes.
So I'm sorry. I guess I can't answer right now.
Yeah, I just wanted to make it clear that a variety of these features seem very similar in Cinder. I'm a Cinder developer, been one for a while, so I'm just trying to understand like what this is gaining me without it or with it.
All right. Okay.
Okay.
So the virtual disk or vDisk has the properties of the size, obviously, the disk type, whether it is the block storage or object storage or file storage, then the residence information, let's say whether the data is residing in hard drives or SSDs, replication factor, so how many copies we need to have of our data that will be stored in this particular vDisk. Then the disaster recovery policy, we mean by that, let's say, whether this vDisk should be data center aware or rack aware or node aware only, or agnostic, as we say. We can, of course, enable or disable the compression, deduplication. That information is this metadata holding for the per vDisk. And also the caching information. If we are having a cache close to application, or we don't require such a close caching mechanism. And in OpenStack integration, by that we actually, when we create a volume, let's say we have a Cinder volume. We need to create a Cinder volume. We just give it a name and well, give the size, obviously, and then we can define the type of the volume. And by the type of the volume, we can actually create today QoS specs by QoS specs to have a different volume types. Like in here, we have a volume which is not very maybe not seen in the back in the back of the rows, in the back rows and over there, but we have a dedupe volume which is in the back end has a, let's say, the replication policy which it should be data center aware. We named it the dedupes. We obviously think that we need to enable the deduplication. Replication policy info, we had a data center aware replication or replication policy, so we can define comma-separated values to data centers where we would like to have this data stored. Another example, perhaps we need to have only the volume that will store the compressed data. So we just have one property in here defined the compression that enables the compression, or we can have a combination of dedupe and the compression, and so on and so on. So basically, we will just define this volume type in here, and then we will create the Cinder volume, and it will be created in the backend in storage tier. It can be also, of course, obviously scripted. Also, we can create these types by plain configuration files, which in Swift case, we will create these properties with a configuration file. And we can create the volumes pretty much the similar way as we created the Cinder volumes. And obviously that can be scripted and automated as well, and also driven by APIs. Customer examples, we have a few customer examples. I guess I need to go through these quickly. We have an example. We have 3 examples in here. The first one, that the customer had a challenge to be to store the block and object files, the VLSI files. It was the manufacturer, the tech manufacturer company that was operating follow the sun model. So they wanted to really have a solution that also supports this follow the sun model, which is which we had. Which we actually were able to support as we offered global or active storage across the globally across the cluster. So we had we offered a solution where the cluster was extended through different continents, and data was replicated over these continents. Secondly, we had the large media company storing media files like videos, photos, some other streaming files. For them, the reissue coding was not a good fit. It had too much CPU overhead or resources requirements, and which didn't fit to their web interface provision very well. And then we actually offered the solution which did the replication in a backend in a storage layer. And the third one was the regional cloud provider. Their challenge was that they wanted to offer the service for customers who had different requirements for the storage. I mean, there was a customer who wanted to have playing capacity. There was a customer, they had a customer who wanted to have a capacity which was replicated, or a customer who had replication and maybe able to clone the data and all these things. So we created a multi-tenant solution for them, which actually enabled these customers to have not the same invoice for their capacity and different functionalities, but each customer had different SLAs or pricing based on their requirements actually for their solution. So in conclusion, in OpenStack environment, as the automation is quite tight between or connection, API-driven connection between the OpenStack orchestration layer and our storage is pretty tight. So we can the storage provisioning can be very fast. Also, we can increase the resiliency to the distribution of our storage volumes across the cluster. And as we do not need any spatial storage arrays in the backend, we just need to have the commodity servers. We can, which some cases you might have in-house already, we can lower the costs by that. And also, And that was my last slide. Thank you.
So we will be here, of course, throughout the day, together with Layer 8, one of our partners here in Sweden. So if you have any more questions, technical one, please drop by and we can try to answer upon them. Thank you. Yeah.
How do you store the data in the backend if you have different storage protocols, like block or file or are they stored in the same way, or are they sort of separated?
Pretty much the access layer, access software is actually translating the front end to the back end, so the data will be sort of stored in the same way. In the front end, access is just different.
How is Hedvig licensed? Terabyte per node or per...
No, it's a perpetual license based per raw capacity. The capacity? Yeah. Raw capacity in the back end on the storage node. So that was the easiest way for us to have a fair license model. Since you're completely the possibility to extend the cluster is endless. We haven't found any. There are probably some physical boundaries.
So it's the same no matter if you use flash or if you use nearline.
Yeah.
It's the same cost.
Yep. And all the functionalities is included, so you can of course deploy, deduplication, and all of those factors.
How does it compare to Ceph? Like, how do you differentiate?
Would you like to answer?
Yeah, if you don't mind.
Sure.
Yeah, first of all, we create the metadata, the disks in the metadata layer only, so we don't actually use the data in a backend unless we are actually writing it there. The Ceph offers still the volumes from their solution. The other thing is that I think the Ceph is hyperscale only solution. We do offer the hyperscale and hyperconverged. Also, we do offer we support also the hybrid solution, which is hyperscale and hyperconverged in the same cluster. We don't care how do you access the data and where do you access the data from.
Smallest possible implementation.
3 nodes. Yeah, you need to have 3 nodes due to the replication factor. So on this.
Actually, the disk should be multiplied by 3, again, due to this replication factor. So we don't want to copy the data to single disks. So therefore, we have 3 disks as a minimum requirement per node. So 3 nodes and 3 disks.
So if you're interested of trying or have a deeper look at it, we have a lab in EMEA where we give access to customers and partners to try it out. So we do a walkthrough in the lab environment to show how it works, and then we hand over the keys for a couple of days so the customers and partners can play around with it and try it out. Yeah.
I want to spin on to the earlier questions, the one there and Mike's question here before. I looked into a little bit, but I still don't have the question. But I want to spin off, like, say, in the OpenStack, I'm not an OpenStack expert, but I know that we have Cinder, we have Ceph, and we have Manila, and we have Swift interfacing to all these. What would you say would be the key point for choosing Hedvig to replace these kind of obvious answers to most storage questions within an OpenStack solution?
To provide a distributed storage platform, so that the storage solution that is active across the whole cluster, and the cluster is built over the multiple data centers.
Okay, multi-datacenter clients.
Exactly.
Is that because of Ceph for Ceph objects, or they need to have a synchronous replication for acknowledging, and you only require semi-synchronous?
Exactly.
Okay, thanks.
Sorry, but I think like the big difference that I would say here is, because I still view this pretty similar to Cinder, just that Cinder is not on the data path. Cinder is completely the control path, but it's also distributed, and it relies on the implementation themselves of the block storage solutions themselves to do all of the, like, it's the control part of Ceph. So what Ceph does best is replicating its data and having that distributed. The control plane, Cinder, that's all it is. Nothing to do with the data path at all, because you talk directly to the block storage layer. It's completely out of the data path, which is exactly, I think, how you want it. And just leave the implementations to do what they do best, while still avoiding all of it.
Right.
But it's like I said, I think what this provides, which Cinder doesn't provide, is from the data path layer, it provides a translation for like the different protocols. That is one thing I saw for it. But
For sure, yes.
yes.
Can we still take it offline? I mean, I'm getting interested of that.
I will also say that Cinder does not support the idea for replication across data centers, because once again, it relies on the implementations to handle that.
Mm-hmm. We have a question.
So let's say I have 2 data centers, and I own data center 1. There is another organization that owns data center 2. and they have some data set that they don't want me to access, but we still want to have some kind of federation, so I can send, for example, a Docker container to do some analysis on this private data set and get the results back. Do you have any kind of feature that would solve this problem? Because I find it very hard to solve.
You have 2 data centers?
Yeah, and then I want to send, for example, a Docker container that does some analysis on data center 2, and I want this to be automatic, but at the same time I want to allow to this, the owner of data center 1 to get some restricted data that is in data center 2. But I'm still wanting to do it automatically based on an access control list, so something like this.
I mean, you can create this vDisk which is accessible from both data centers. That is something that you can do for sure. If now the second data center server will write some additional or incremental data to the volume, so you would not like this first data center to see this data, or did I understand correctly?
Exactly, but I still want, maybe the owner of data center 2 still wants to allow to do some analysis on this data, not to give the access to the data, so I can't copy the data and send the data, but I can get some analysis from the data.
That's an architecture question. Let's take it offline as well, I guess. All right, thank you.